Bismillahirrahmanirrahim. Welcome back. Today I'm going to present you the fourth type of band pass modulation and demodulation technique, which called quadrature phase shift keying. Quadrature phase shift keying. We're talking about four angles or four shift keying. Quadrature phase shift keying. In this case, we have 90-degree phase shift instead of 180-degree, which we used in the phase shift keying previous lecture. Here we are talking about 90-degree phase shift. Here also we will assign 2 bits for each phase. We'll talk about 0, 0, 0, 1, 1, 0, and 1, 1. This will be non-return to 0 level. And which here we have the phase, which means that for this case, we'll talk about this is the 0, and we'll talk about 0, 0 means here that we are talking about the 45-degree angle, 45 angle here, and here we're talking about 135-degree. Here we're talking about 225-degree, and here 315 degrees. So we are talking about different phases. This also here in this case we will use 2 carriers. The in phase carrier here we will use also 2 carriers. In phase carrier, which we will assign as the most significant bit later on, most significant bit, and we will use the quadrature carrier, the quadrature carrier. This is the I carrier and this is the Q carrier. Between them we have 90-degree phase shift. So here we our I carrier, in phase carrier, and here will be our quadrature Q carrier, and you will assign 0 for this level, and here we have also 0. Here we have 1, and we will have here 1. So if you are talking about the 0, 0, which means a 45-degree phase change. If we are talking about 0, 1, we'll talk about a 315-degree phase change. We'll talk about 1, 0 will be 135 phase change, and if we talk about 1, 1, we will have 225-degree phase change. So in this case we'll assign 2 bits for each phase, which means that twice data can be transmitted compared with the phase shift keying, or the same data can be transmitted with the half phase changing, which means also that we can minimize the transmission bandwidth of the channel. So we are talking about the benefit of the quadrature phase shift keying compared with our typical or classical traditional phase shift keying here, that we assign 2 bits for each phase, so which means that twice data can be transmitted compared with the phase shift keying, or the same data can be transmitted with half phase change comparing with the phase shift keying, and in this case we can reduce the transmission bandwidth. Now I am going to draw the block diagram of our transmitter or the modulator. We will have 2 modulators. First one, the I modulator. The second will be the in-phase modulator, The second will be the Q modulator. Yes, we have the first modulator. We have the carrier input here, carrier input. And we apply here the in phase. Also here we have talking about the data input or modulation input. Here the same as we use in phase shift keying, we have the unipolar data input. We have to apply it to unipolar to bipolar data converter, unipolar to bipolar converter in order to have plus V and minus V. And here we have another modulator for the quadrature input, the Q, the quadrature component of the carrier. This is the carrier input. And here again we're talking about unipolar to bipolar converter, and here the Q data input, unipolar data input, then unipolar to bipolar converter, then we're talking about now return to zero level. Then we have summing amplifier for both cases, summing amplifier, and the output will be quadrature phase shift key, QPSK, quadrature phase shift key. In this case, or the traditional one, we will have a problem. The receiver will find it's difficult to distinguish between the following angles. It will find difficult to distinguish between 45 degree and the opposite one, which is 225 degree. Also, it will be difficult or impossible to distinguish between the angle which is 135 degree and 315 degree. So we have 4 interpretations for the angle. Only one of them is correct. In this case, in order to solve this problem, we will assign not the phase, we will assign that 0, 0 means specific change in phase, comparing with this one. So the modification, in order to solve the problem of phase ambiguity, we called it as phase ambiguity. So in order to solve this problem, again, I'm going to compare this new technique with the previous one. So non-return to zero level. So we're talking about 0, 0, 0, 1, 1, 0, and 1, 1. So in the previous one, the old meaning means that the phase of this one, the phase. We are talking about 0, 0, 0, 1, and 0, 1. Again, we're talking about 0, 0 means for this case 45 degree. We're talking about also 0, 1, 315 degree. We're talking about 1, 0, 135 degree, and 1 means 225 degree. This is the old meaning. Now's meaning, new meaning is specific change. The change in phase. Now I'm going to write specific change in phase. So the phase change. If we will talk about 0, 0 means no phase change, no change in phase. Talk about 0, 1, for this case will be 90 degree phase change. Talk about 1, 0 for us will be 180 degree phase change. If we talk about 1, 1 means 270 degree phase change. In order to solve the phase ambiguity. Which means that we cannot distinguish between this and this and this and this. So we have only 25% of correct decision. So instead of deciding that 0, 0 means that 45, the phase 45, we will assign that 0, 0 means no change in phase. 0, 1 means 90 degree phase change. 1, 0 means 180 degree phase change, and 1, 1 means 270 degree phase change. Now I am going to draw the block diagram of the modified modulator of the quadrature phase shift keying in order to solve the problem of phase ambiguity. So here I'm going again to draw the modulator, first modulator and the second modulator. Here we have to talk about the I carrier in phase. Carrier, this is the carrier input, and this is the data input. Here unipolar to bipolar converter again, but here we will talk about the most significant bit. Here again we have the Q carrier, quadrature carrier input, and degree phase shift with respect to the in phase 1, and here also unipolar to bipolar converter. Then we have non-return to zero L signal input here. But here we'll talk about least significant bit. For the quadrature carrier, we'll talk about least significant bit. Here for the in phase we'll talk about most significant bit. This is the modulator, and we'll apply it together to summing amplifier in order to obtain the quadrature phase shift keying signal. Now I'm going, the final step will be our receiver or demodulator, which typically look like the demodulator which we use in phase shift keying, but here we will have two channels. So I am going to assume that we have quadrature phase shift keying signal. It will be applied to quadrature phase shift keying demodulator. Then we have here, we will talk about two channels. Channel number one for M phase, and this is two for the quadrature components. Then we'll talk about low pass filter number one. Then we'll talk about low pass filter number two. Then we'll talk about voltage comparator number one, the same as we use in the phase shift keying. Here also voltage comparator will be voltage comparator number two. Then here we'll have differential encoding, D-bit, differential encoding, which is called D-bit. And the output will be, the final will be null return to zero. The output here, null return to zero, and signaling that our data output. So the quadrature phase shift keying waveforms applied to quadrature phase shifting demodulator. The output will contain the remnants of the carrier, and the output will be rounded. So here we'll have two channels because we're talking about the M phase channel and the quadrature channel, 9-degree phase shift between them. First one, we have the low pass filter number one for the M phase channel, which removes the carrier components. Low pass filter 2 for the quadrature channel to remove the carrier component, the remnants. Squaring up the signal, we use voltage comparator. That's typical as we used in the previous phase shift keying, and differential encoding in order to have the null return to zero L or level output, which is data stream which we transmitted. This is that's all for quadrature phase shift keying. And the main advantage of this technique comparing with the phase shift keying, that we assign 2 bits for each phase, which means twice data can be transmitted, which means that we can minimize the channel bandwidth or transmission bandwidth. This is a modification for our previous phase shift keying. I hope you will understand this lecture. If you have any question, don't hesitate to contact me. That's all for now. See you next lecture. Bye.